Hello, good afternoon, everyone, or good morning, or good night, regardless where you're located. Hello, and welcome to the first Data Science Summer School organized by Hertie School Data Science Lab and Data and Methodology Center at the Scripps Cluster of Excellence. I would like to thank our funders, the Scripps and the Stifterverband, for their generous support. And I'm extremely happy to see you all here today, both on Zoom and on the parallel session on the YouTube. And I would like to note a couple of technical and organizational details. If you're in the Zoom meeting, you're all muted and your cameras are off upon entrance. Please do not unmute yourself and do not turn the videos on unless you have a question. We really ask you to put the questions in the chat, and that way it's going to be easier to handle the questions both for the instructor and the TA. But if you really want to ask a question, you can raise your hand, and whenever there's going to be a good time, we will let you speak and ask your question and turn your camera on if you want. If you're on YouTube and you want to ask a question, you can leave the question or the comments in the chat, the live chat, and we will handle the questions as well. We will either try to respond them ourselves or we will direct them to the instructor or the TA. I also want to remind everyone that the Zoom session is being recorded, and thank you so much in advance for following these rules. And without further ado, I want to introduce you the 7th workshop in this summer school series. It is web scraping with R, and let me introduce you Dr. Rochelle Terman. She's an assistant professor in the Department of Political Science at the University of Chicago and a faculty affiliate with the program on computational social science at the University of Chicago. She specializes in international relations with an emphasis on international norms, human rights, and the Muslim world. She's also interested in computational social science and teaches courses on machine learning, text analysis, and programming. Rochelle, the floor is yours. You can share your screen now, and thanks so much, everyone.
Thank you very much, Olga, and thank you to the organizers of this fantastic looking school. I welcome everybody. Unfortunately, there are too many of you to get to know you more in the beginning of class, but I really hope that you enjoy this workshop, and please feel free to reach out if you have any questions throughout. So I'm going to go ahead and start sharing my screen, and we're going to start just with an overview of the class and kind of how things are going to run. It seems like, Olga, it seems like the host has disabled screen sharing for me.
Yes, you should be able to share now. Yes.
Okay, great. So can everybody see my slides? Pete, can you give me a thumbs up if you can see it?
Yes, it's perfect.
My purple slide? Okay, great.
Yes.
Wonderful. So this class is on web scraping in R. And I know that Olga already said a little bit about me, but again, I'm Rochelle Terman. You can call me, refer to me as Rochelle. I'm assistant professor at University of Chicago in the Department of Political Science. At one point, way back in the day, I was a web developer, specializing in Drupal and WordPress and open CMSs like that. And so web scraping has a particular place in my heart. Today, I program mostly in Python and in R, actually more probably in R these days. I originally developed these materials for Python. And so if any of you are interested in seeing a version of this class that's in Python, please feel free to reach out over email, and I'll be happy to send those to you. As Olga mentioned, my substantive interest is in international relations and international norms. And I am unfortunately not going to be able to answer all of your questions today because I don't think that anyone will be able to answer all the questions of a class this size. But I will absolutely try my best. And if there's something that is come up and I don't know the answer, I'd be happy to check it out and then get back to you. Pete, would you like to say a couple words about yourself?
Sure. Hello, everyone. My name is Pete Cuperno. I'm the TA for this session. I'm a PhD student at the University of Chicago, where Rochelle is one of my advisors. Really excited to be here with everyone today, and looking forward to a great session.
Great. Thank you, Pete, for joining us. Okay, so as social scientists, we know that there is a ton of data that's available on the web that we might be interested in using for our scholarship. These include social media, news media, government publications, organizational records. More and more data and more records are coming online. And there are two broad ways to collect these data. One is through what's called web APIs, or application programming interfaces. These are machinery that is developed mostly for computers or for applications, like apps on your phone, but we can piggyback onto them to collect data as social scientists. The second way is through web scraping, meaning that we're looking at user-facing websites that were designed for humans, but we're going to write a computer program that will automatically collect those data. And as I will be re-emphasizing throughout this class, a rule of thumb is that we want to check to see if there is an API first that provides the data that we're interested in. And only then, if we find out there's no API, should we look into scraping. So for today's class, we're going to split it up in those two broad buckets. So for the first couple hours, we're going to be talking about APIs, specifically RESTful APIs. I'm first going to explain what an API is and how it works. And then we're going to be writing an API query to extract data from the New York Times article API.
Excuse me, Rochelle.
Yeah.
Sorry to interrupt. It appears as if the slides aren't advancing on the screen share. It still is on the About Me slide.
Oh, dear. How about now? Outline the course?
Still says About Me, at least on my end.
Oh dear. I'm not exactly sure why that's happening.
No, it did just jump forward.
Okay, I think I understand. Thank you, Pete. And thanks for all of your patience. We're probably going through some hiccups, at least in the beginning of this class, but hopefully things will go a little smoother as time goes on. So as I was saying, we're going to split the course up into two parts. The first part we'll be talking about RESTful APIs, and the demonstration that we're going to use is to collect information on New York Times articles. Then we'll take a break, and then the second half of the class we'll talk about web scraping. So in order to get a grasp on web scraping, we first need to understand how HTML and CSS work. And then we're going to inspect a website using something called Selector Gadget in order to understand its underlying structure and to identify the elements that we're interested in. And then finally, we'll write a program that scrapes multiple pages on a website using R. These materials that I kind of put together are available online, and they're not available yet. I'll talk about that in a second. But in those materials, I've added a couple other lessons that we won't be talking about explicitly today, but that you might want to work through on your own. So one is a plug and play R package for Twitter's API. Plug and play package meaning that someone wrote an R package that kind of wraps a lot of these common API tasks into functions that we can just kind of install and use. So that is called Twitter, I believe. And that lesson kind of walks you through how to use that package to collect data on Twitter's API. And then the second is a lesson on something called Selenium, which helps us extracting websites that use a lot of JavaScript and that are super interactive. Very interactive sites have particular challenges that we can't overcome using a more traditional web scraping strategy like the one that I'll be covering. And so if you're looking at a site that has a kind of more interactive structure, you might need to use something called Selenium. Okay, so typically when I teach a class like this, I like it to be very interactive, kind of combination of lectures and then coding exercises, and we'll have students follow along on their machines. But this is not going to work for a class of this size. And the reason for that is twofold. So for APIs, in order to use an API, you need what's called an API token or an access token. And each individual needs to have their own individual token. And so just for the sake of time and the class size, it's kind of unfeasible for us to all get tokens in time. But actually more importantly is the web scraping portion. And if for the web scraping portion, if we all follow along at the same time, what's going to happen? We're all going to ping this poor website, hundreds of us, at the same time. And that is going to overload that website server, and it's going to cause the website to crash. And if the website crashes, obviously our workshop is going to be interfered with, but also all of those websites users are going to have their experience interrupted as well. And so it's generally just impolite and rude to ping a website, kind of hammer it in that fashion. And so I'm going to ask that all of you today watch me and watch my computer for the coding portions. We'll hopefully kind of make it such that you still kind of get that same experience of if you were coding it yourself. But I ask that you not follow along on your screen, that you don't execute the code for the reasons that I just mentioned. But we still kind of want you to have those materials and those resources. And so I'm going to make all of the materials available after class. And so there is a GitHub repository. If you navigate to that repository now, you'll probably get a 404 error because we've made it private. But we're going to make that public as soon as the class is over, and you can work through the materials on your own. And those include all the materials on APIs and web scraping and Selenium and other things. Another resource that you might find helpful is a chapter of a textbook that Pete and I put together. I'm going to navigate over there. And Pete, I see that folks have asked if we could put the links in the chat. So if you wouldn't mind doing that. So this is we're going to be working through the same materials that are included in this chapter. And so if you ever want to kind of go back to this as a resource or as a reminder of what we talked about, you can do that, or you can either follow along maybe in another window in addition to Zoom. So those are the kind of the two resources for you. So this is available now. And this GitHub repository, the GitHub repository is going to be available after class. I'll kind of just show you quickly what it looks like. Of course, it says page not found. But if I'm not in an incognito window, oops, it will show you all those materials. I'll show it to you during the break, and I'll put that link in the chat as well. Oh, thank you, Pete. Okay. Are there any questions at this point about how the class is going to run? Yeah, thank you, Hannah. So the GitHub repository, I'm going to make available maybe like no more than a half hour after class is over. Okay, great. Well then, we can move on. I'm going to take a quick 3-minute break to grab some water. And when we come back, we'll dive into the API lecture. And if you have any questions in the meantime, please feel free to put that in the chat. So we will return in 4 minutes. Okay, welcome back, everybody. Okay, let's go into our first lesson on APIs. Okay. Can everybody see my purple slide? Give me a thumbs up in the chat if you can.
Yes, we do.
Okay, great, thank you. Okay. Okay, so as I mentioned, there are two broad ways to collect data off of the web or off the internet. And we're going to start with APIs because we really prefer collecting data through APIs if it provides us the data that we're looking for. So if we can collect the same data through the web versus an API, we always want to pick an API. It tends, and hopefully the reasons for that will become clear as we continue throughout the lesson. But in brief, it's just the data is a lot more structured, and it's more straightforward in many ways than screen scraping. Okay. So an API stands for Application Programming Interface, and broadly defined, an API is a set of rules and procedures that facilitate interactions between computers and their applications. So a very common API is a web API, which, among other things, allows users to query a remote database on the internet. Now, web APIs can take a variety of forms, but the vast majority adhere to a particular style or flavor known as representational state transfer, or REST. So what makes these RESTful APIs is that they're convenient. The reason that they're convenient is that we can use them to query a database that's on the internet somewhere using nothing but a particular URL. So RESTful web APIs are actually all around us. So if we consider a simple Google search, we might type in Golden State Warriors in a Google query. And then if you look at the address bar, you'll see that the address will be something like google.com / golden state warriors, or actually it'll start with hashtag q golden state warriors. So that address is Google's way of telling its databases, hey, this user is looking for information on this particular search term, Golden State Warriors. And in fact, it looks like Google is making that query using a particular pattern. It's taking those search terms, it's separating each one of them with a plus sign, and then it's appending them to a link, www.google.com /#q equals. And so all we have to do to be able to change our search term is to change the URL. So learning how to use RESTful APIs is all about learning how to format those URLs so that we get the information, the exact information and response that we want. So let's go through and get on the same page with some basic terms. A URL, we're probably all familiar with that term, but maybe we're not familiar with exactly what it means. It stands for Uniform Resource Location. And it is a string of characters that, when interpreted via the Hypertext Transfer Protocol, or HTTP, points to a data resource, notably files written in hypertext markup language, or HTML, which is a subset of a database. That is often called a call when we put in that URL into our browser. HTTP, which is kind of the structure that runs the entire internet, has different methods, or sometimes what's called verbs. So the one that we're going to be working with the most today is called GET, the GET request. A GET request is a representation of some data resource corresponding to a particular URL. So the process of executing a GET method is referred to as a GET request, and that's the main method that we're going to use for querying RESTful databases. There are other methods that sometimes you'll see, like a head, post, put, and delete. These are common methods, but they're not typically used for querying a database. Okay, so how do GET requests work? Well, we can go back to using a web browsing as an example. So surfing the web is basically the equivalent of sending a bunch of GET requests to different servers and asking for different kinds of information that are written in HTML. So suppose, for example, I want to look something up on Wikipedia. The first step would be to open my web browser, type in www.wikipedia.org. I hit return, a few milliseconds pass, and I'll see a web page. So even in that very simple process, several different things happened between me hitting return and the page rendering on my browser. So in order, the first thing that happened is that the web browser took my character string, my URL, and then used this tool on my computer called curl to translate that URL into a properly formatted HTTP GET request. And then it submitted it to the server that hosts the Wikipedia homepage. So you can think of this as kind of like making a call to Wikipedia. Hey, I'm, Rochelle Terman wants this particular homepage. Can we give it to her? The second step is that after receiving this request, the folks over at Wikipedia, the server, sent a response, sent an HTTP response, which once we get it, curl then extracted into the HTML code for the page. And that HTML code is partially shown here. But of course, we're not typically interested in a raw HTML page. We want to see that HTML code parsed and executed by our web browser to render a page that we see here. Okay, so those are the three steps. We took a string and made a GET request. The server received it and sent us back HTML, and then our browser translated that HTML into pictures and links and images. So the process of web browsing that I just described is a pretty good analogy for the process of querying a database using an API. There are just a few adjustments that we have to make. So for example, the URL that we supply has to be constructed in a particular way so that the resulting request can be interpreted and successfully acted upon by the server. In particular, it's likely that the character string has to contain or encode some search terms that we want, or maybe a particular filtering parameter that we're interested in, or perhaps some authentication codes. And all of those terms are specific to the particular API that we're using, but they're also similar across a lot of APIs. Unlike web browsing, we're not going to be getting HTML back, or we're rarely going to get HTML back. The content of the response is likely to be some kind of raw text like a CSV, XML, or probably most commonly a JSON, which stands for JavaScript Object Notation. We'll talk a little bit more about that once we get to the code. But basically, it's going to give us back all of these kind of raw text that's really messy and that we have to parse into something that is actually usable, such as a spreadsheet. So after, whereas our web browser parsed an HTML code, we can't use our web browser anymore. We have to use something like R or Python or some other kind of programming language to parse the server response and to convert it into a format that is usable for us as social scientists, like a data frame or a database or a matrix or a spreadsheet or something like that. Okay. Just to take a step back, and it might be helpful at this point to talk about why APIs were needed in the first place. So for example, APIs were constructed not for social scientists, they were created for app developers. Why? Well, imagine you go to Twitter, or excuse me, well, imagine you go to the New York Times and you see an article that you think is really important, and you want to tweet about it. Well, typically on the New York Times page, there's a little button or icon that says tweet this, right? We're all kind of familiar with this. And then you click on that button, and then what happens, usually a window will open up that magically fills in, signs you into Twitter, and even like writes the tweet for you about the particular article. So what was happening there? The New York Times was communicating to Twitter, right, and sending it data. That requires some form of communication between Twitter and New York Times. The New York Times has information in its database that it wants to share with Twitter and put in their database. And so how is that going to happen? Well, one way that they could do it is just to make their databases completely open for anyone to look at. But that's probably not very wise because they're going to be giving away the store, right? They make money on content and they don't want to just give away that content, either Twitter or New York Times, for free. And so instead, they create these things called application programming interfaces that allows those two databases to talk to each other in a particular way. And we see application programming interfaces all over the place. So, and on our phones, if Facebook can contact our contact list on our phones, for example, if we give it permission, that requires an API because Facebook, the app, is communicating with contacts on our phone. Or I have like a step barometer that calculates how many steps I take a day, and that communicates with some kind of fitness app. There are all sorts of apps that want to be able to communicate with each other. And in order to do that, they use APIs. That's why most of the APIs that you see out there in the universe are designed for app developers because they want people to create apps that work with whatever database that they're offering. But there are some APIs that are specifically designed for researchers. So here are some APIs that might be useful to you. So today we're actually going to be working with the New York Times article API, which was not designed, I think, for researchers in mind, but more for social media platforms and things like that. But it can also be helpful to us as social scientists because we can collect metadata about articles, such as the titles of articles, summaries of articles, and so on, from all New York Times articles in their archive. Some other APIs that folks might be interested in, I just collected kind of a sundry here. One is the GeoNames geographical database. So this includes a lot of geographical information for all countries and locations. The Manifesto project is an API that provides text and other information on political party manifestos from around the world. The Census Bureau provides data sets from the US Census, and there are a lot of others. So just to address a few of the questions in the chat. So does the API allow to communicate across paywalls as well? Some do, but then they'll ask you to sign in first, for example. So, the Twitter API, for example, it's not behind a paywall, but it is behind an account. You do have to have some kind of an account. And so if in the example that I was using earlier, if you see a New York Times article, you want to share it on Twitter, you click the little tweet button, that the Twitter will either automatically sign you in, depending on your preferences, or it will ask you to sign in first. And so that basic protocol where it's kind of going to ask you to sign in to your account, that can occur across paywalls as well. So there was a question, you talked about client browser and server communication, but where is the API sitting on? That's a good question. So the API, the actual kind of technical infrastructure of the API lives kind of in two places. One is the server. So the New York Times has to create an API, right? That is designed to work around its database. But the actual way to access that API is through HTTP methods that run the entire internet, if that makes sense. And so you can, the analogy, perhaps could be, my university has to create a building and that building lives on the campus, but I'm going to use the public roads to get to that building. So we're in this analogy, the roads are kind of the HTTP methods that we all have access to on our computers. If you have a web browser, you have the internet, and we all have hidden programs on our computer that are able to work with those methods. And then we're going to use those to interact with an API, the technical infrastructure of which lives on a server, like the New York Times server or the Twitter server or whatever. Yeah, there are also, Pete, you accidentally direct messaged this to me, but I'm going to share it with everyone because it's a good answer. So many websites like Twitter have both free and paid APIs. So the free, for example, Twitter is a great example. So Twitter has a free API where you can collect only certain amounts of information, like only the tweets in the last 7 days. But then they also have a version of an API that's a lot more powerful where you can collect a lot more information. And that is kind of a premium API that costs a lot of money. Okay. So there are a lot of other APIs. APIs pop up every day. Spotify has a great API that's kind of fun. IMDb, movie database, has an API. If other folks have used APIs that they think are kind of fun or interesting, I would encourage you to put that in the chat. Olga brought up a good point, which is that Twitter just changed or just created a new version of their API that's designed only for academics. That's kind of special because, as I was just explaining, most APIs are not designed for academics in mind. But I think that Twitter realized that a lot of scholars were piggybacking off their APIs and had special needs. And so they created an academic Twitter API, which is free, but you do need to prove that you're an academic in order to access it. Pete, do you have any other fun APIs that you'd like to share?
Well, for teaching purposes, we often use the IMDb API. Spotify also has one, but many news outlets have them as well. I know New York Times is a go-to one for us, but to my knowledge, there's a handful of other outlets that offer APIs too.
Oh. Okay. Are there APIs available for Scopus or Web of Science searches? I don't know, but we can look into that. I actually would not at all be surprised if Web of Science offered an API. Okay, let's continue on. So most APIs require some other kind of user credentials before you can use them. Okay, this is sometimes referred to as a key or an access token. As I just described, most APIs are set up for developers, for app developers. And so when you are credentializing with an API, you'll often see you have to fill out a form and it'll ask that you register with the organization. And so because most APIs are set up for developers, you'll likely be asked to register an application. What's the name of your application? And all of that really entails is just coming up with a name for your project. So we're not here, most of us, we're not creating apps, but we are using this for our social science project. So I just put in like the name of my class that I'm teaching or a project, the academic project that I'm using this for. And you'll also probably be asked to provide your name, your organization, and your email. Some of the more popular APIs, like Facebook, will require additional information, especially after their recent scandals with Cambridge Analytica, all of which used APIs to do their nefarious things. So sometimes they'll ask that you provide a phone number or a physical address. Okay, so once you have successfully registered, you'll be assigned one or more keys or tokens or other credentials that you have to supply to the server anytime you make an API call. And that's because they want to make sure that users are not abusing their data access privileges. So because we're going to be using a computer for this, we could make, 1,000 API calls a minute. But that's going to hammer their servers, and they don't like that. And so a lot of APIs will limit the number of calls that you can make via rate limits. Okay, so rate limits govern the total number of calls that can be made over a certain interval of time. So the last time I checked, this might have changed, but the last time that I checked, the New York Times article API had relatively generous rate limits. They allowed you to make 4,000 requests per day and 10 requests per minute. So that means that we need to, if we're writing a program that makes multiple API calls, we need to sleep 6 seconds between calls in order to avoid hitting the per minute rate limit. Okay. So there are two ways to collect data through APIs in R. So the first is through what are called plug and play packages. So many common APIs are available through user-written R packages. These packages offer functions that wrap API queries and format the response for you. And so they're usually a lot more convenient than writing our own query. Think about this as like, are you going to make dinner from scratch, or are you going to go to the grocery store and get your pre-cut vegetables or things that are kind of half cooked for you? The plug and play packages are a lot more convenient, and so it's worth searching around for a package that works with the API that you're interested in. If there is no package, plug and play package, then we need to actually write our own API request and format the response ourselves. And this is a little bit trickier. It involves a little bit more programming knowledge and practice in R, but it's definitely doable, even for folks that are relatively new to R. Okay. And so with that, I'm going to see if there are any general questions about APIs before going over to the code. Is there an API data which is collectible, but that we are technically not allowed to use by the law? I don't think so. I think that if they allow you, like if the server allows you to collect material, unless the material itself is illegal, then there's no like legal barrier to using an API like there might be for web scraping. I hope that makes sense. Any other questions? So Baptiste will send you the links to the GitHub repository and the chapter. Just be aware that the GitHub repository is not public yet. I'm going to be making it public right after the workshop is over, because we can't have students follow along. Otherwise, we're going to destroy these core APIs and the website servers. Okay, well, if questions come up, please feel free to put them in the chat. And I'm going to take a few minutes here and switch over to R. So hang with me for just a minute. Okay, I'm going to first share a web browser and talk to you a little bit about the API that we're going to be working with, and then we'll move it over to RStudio. Okay, so the API that we're going to be demoing with is called the article search API from the New York Times. And thankfully, this API is very well documented. I find that oftentimes when working through APIs, 80% of the struggle is reading documentation. Documentation is very, very important when working with APIs, because although a lot of the infrastructure is similar across APIs, you still need to know what that specific API wants from you. And so reading documentation is going to be super important. But reading documentation is not a skill that we were all born with. It's actually a skill that we develop over time and that we have to practice and learn. And thankfully, I find that the New York Times documentation, it's a little intimidating looking, but it's pretty intelligible. And it's written kind of for, it's not written in too technical of a language. But this is the kind of basic kind of walkthrough or overview of the API. And we can also actually try it ourselves using this interface here. And both of these links will be available in the materials. If you want to get your own API token, then all you have to do is follow the instructions in the Get Started page. So it's developer.newyorktimes.com/get-started. I'm going to throw that in the chat. For some reason, my paste doesn't want to work. Maybe this will work. Okay. Pete, if you could just throw the link in there. My apologies. My computer doesn't want to paste for some reason. The developer.newyorktimes/get-started. That will, thank you. You can follow those instructions to get an API key. And then to Olga's question, is there a list of APIs? Yeah, a great resource is called the Programmable Web, if I spelled that correctly. So the Programmable Web is kind of the closest thing to a directory of all the APIs out there. So they're in addition to kind of news and tutorials. And so that's a great resource as well. Okay. So Olga, I see YouTube. What about the Facebook API? Could you maybe unmute yourself and explain a little bit more what you're asking?
I think there is someone on YouTube just asking about the details about Facebook API, whether it can be used or something like that. Yeah.
Thank you. Yeah, so, you know, again, each API is is different and they're going to offer you different things. And I know that Facebook probably has several APIs. And so, you know, I would just kind of refer you to their documentation to know what you can actually access. Because each API is not, they're not going to give you everything. So for example, in the New York Times API, they're not going to give you the entire text of an article. Why do you think that is? Well, if anyone can use their API to collect all the text of all their articles, then again, they're kind of giving away the store. They make money on their content. And so the kind of the rule of thumb is that the more a website relies on its content to make money, then probably the less information that you're going to be able to get through an API. And so we're going to actually see through the New York Times API what we're actually going to get back. And you can actually see here once we actually work through this, what we're going to be able to get. So we're going to be able to get the headline, we're going to be able to get the date of the publication, the type of the document, the news desk where it was from, the word count. But with all of these things that we get, one thing that we're not going to get is the full text of the article. And that's very common for media APIs. With Facebook API, you can imagine the same thing. Anything that's private, they're not going to give you through an API. You're only going to be able to access public information, and probably less and less of that. After the Cambridge Analytica scandal, they're probably kind of cracking down on really what you can access through the Facebook API. Okay, I'm going to switch over now to R. Okay. And just as a kind of a meta point, all of the code that we're going to be creating in this class are going to be available in the GitHub repository materials that I will post after class. So there's no need to kind of frantically type or take notes on the code that I'm writing. And in fact, I think it would be a lot better of a learning experience if you just kind of watched my screen, made it full screen, and then you can always refer back to the code later. So I'm going to make my text nice and big here. And let's try our first command. Can folks put in the chat whether that size of the font is working for them, and everyone can actually see our studio pretty well? Okay.
It's fine.
Okay, thank you. All right, if something comes up, let me know. But this is going to be our web scraping demonstration for the New York Times API. I'm just going to quickly save that in case I crash. Okay. So for this unit, we're going to need the following packages. So we're going to be using tidyverse, which is hopefully folks are familiar with, a lot of helpful packages to manipulate data. We are also going to be using a few tidyverse packages that are not automatically loaded. So we're going to be using Stringer. We're going to be using the HTTR library to do our GET requests and to kind of work through HTTP. We're going to be using a package called JSON Lite, which helps us manipulate JSON files and JSON text. And then one kind of final package is Lubridate, which is a really helpful package for dates. Stringer is a package that helps us manipulate strings. It's part of the tidyverse package, or it's tidyverse universe, but it helps us with string data and character data. Okay. All right. So the first thing that we need to do, oh, oh yes, thank you.
I think it was about the spelling, yeah.
Oh, thank you very much. I didn't read carefully enough, thank you. And that will happen a lot throughout the next hour, our typos. So I appreciate everyone calling me out on that. So the first thing that we're going to be talking about is constructing the GET request. So this is probably the most challenging part of using an API is learning how to format this GET request URL. So the basic task is just to create a URL, but it has to be a very particular URL. And that URL is going to contain all the information and all the search terms and queries that we are looking for. But it has to be formatted in a particular way. And even though there's common architectures across APIs, each one kind of has its own quirks. And so most APIs kind of need the following things. We're going to need an authentication key, which I've already registered before class. We're going to need something called a base URL, which is kind of like a link stub that will be at the beginning of all calls for a given API. We're going to have our search parameters, and these are going to be appended to that base URL, and it's going to tell the server what exactly to extract from the database. It's basically a series of filters that point to a particular part of the database. And then some URLs, you can specify the response format, which is, typically either do you want to get a CSV back, do you want to get a JSON back, do you want to get XML back, and so on. Okay, so let's go ahead and put some of those things that we know that we're going to need into some variables. And so I have my key copied here. Okay, so this is my particular unique API key that points right to me. So don't take my key. We're going to put in a base URL. I'm going to store that in a variable called base.url. And this, I looked at the documentation to find out what this base URL is. And it is http api.nytimes.com/something. So I didn't just know that base URL off the top of my head. I read the documentation and it told me what the base URL is. And notice that in this base URL, it also includes what the response format is. It's in JSON, so we don't need to configure that directly. And then finally, let's put in a search term, something that we're interested in here. Okay, so I am going to put in Mearsheimer. John Mearsheimer is a famous international relations scholar and one of my colleagues here at the University of Chicago. And so I think it would be kind of fun to see how many articles featured John Mearsheimer in the New York Times over time. Okay. So we're just make sure that we run all of that. The key is the same thing as the token for the most part. Yep. Sometimes token is, could refer to both a public and a private, but for our purposes, when I say key, I mean the same thing as token. Okay. All right, so now we're ready to actually make our request. And we're going to be using the get function from the HTTR package. We're going to store this in a variable called R. And so that the function again is get, okay? And that comes from the HTTR package, and it basically constructs the GET request. And we have to put in a few things here. So the first thing that we have to put in is the base URL. Okay, and then we're going to put in something called a query. And the query has to be constructed as a list, a named list, where we have on each item on the list, we have the name of the attribute that we are entering. And then on the left side is the value. So let me just walk through this really quick. So these things that are kind of in tick marks, Q and API key, these are a key value pair. So if you're familiar with programming, you're probably familiar with key value pairs. And think of it as when we're filling out a form, any kind of web form, it's going to ask you name, and then you type in Rochelle Terman, year of birth, 1986. So in that example, name would be the key, Rochelle Terman would be the value. Date, year of birth would be the key, 1986 would be the value. And the same kind of principle applies here, that the API is asking us for certain information that it has names for. So Q is a very common kind of name for whatever we're searching for, the search term. And so I have to put in, okay, the value for Q is going to be my search term, which I entered wrong. And remember that our search term I've already assigned as Mearsheimer. Another thing that it's going to ask us for is API-key. And I'm going to put in my key. I knew that the name of this attribute, API-key, that it was precisely this, that it wasn't API_key or API.key or API, it's API-key. I knew that by looking at the documentation. Okay, so I referred back to the documentation. It told me that it is looking for specific things, namely Q and API-key. And so I'm going to then give it those values. Okay, let's run that. And now we have this object here, R. It's a list of 10. Let's see one of the things that first comes up, which is the URL. And so this URL, okay, that you see here, that is the GET request URL. Okay, we can put that directly into a web browser, hit enter, and we're going to get information back. Okay. Actually, let's go ahead and try that. That's going to require me switching to another window, but I think it'll be worth it. Okay, so you'll see here that I just copied and pasted that URL that I got from R, and I hit enter, and I got all of this text. That looks like a mess. This is the JSON text that contains all the information that New York Times is sending back to us. We're going to be parsing this text a little later. But you'll notice here that this is a good sign. This means that our GET request worked and that we're getting information back. What if we wanted to add a date range? So I put in the main query, which is just the search term Mearsheimer. But what if I only wanted to search Mearsheimer for a specific year, like 2005? How would I go about doing that? Well, we have to go back and look at the documentation. So to Olga's question, Q is universal, right? I'm really tempted to say that I'm hesitant to say that it's universal. I'm hesitant to say that anything's universal. But Q is extremely common as the key for the whatever search term we're using. But I've also seen like FQ sometimes. So Q might be universal as that particular value. It's certainly very common across a lot of APIs. So here's again the documentation, one of the documentations for the API, the New York Times API. And you can see here are the parameters. Here are those key value pairs that I was just talking about. Here are things that we can kind of put in. So you'll see here, again, on the left-hand side is I'll make it a little bigger. On the left-hand side is the key. And then on the right-hand side, it'll tell you what exactly it's looking for. So the query is looking for a string. You can also have a sort parameter if you wanted to sort by newest or oldest. And so it's only going to accept these following values. And so let's see if it has a date. Okay, begin date, end date. And so begin date is one key value parameter that we can enter. We have to enter a string and it has to be in a particular format. Okay, so this is the particular format that it's looking for. So the 4 numbers of the year and then the month and the day. And then we can also put in an end date using that same format. So let's go ahead and try that out in R. Okay. So if we wanted to add a begin date, I can add another key value pair here. And I think that this was, let me go quickly, begin underscore date. And remember that it's looking for a string. So we have to put this in quotation marks. And let's say we only wanted to search for 2005. So let's search, if we wanted to search only for the year 2005, then we'll specify the begin date as January 1st, 2005, and the end date as December 31st, 2005. Okay, now let's try that out. Now let's look at the URL. Okay, so we're getting a slightly different URL than we did the last time. So just to show you, this is the URL without the date filter. This is the URL with the date filter. Okay, so you can see here that they're basically the same, except we have this extra stuff. We have this and ampersand and begin date, another ampersand, and an end date. And so we can continue adding information here to narrow our search. So for example, let's do one more. Let's say if we actually put this in, we're only going to be getting 10 results. And this is just how the New York Times API works, that it's only going to return to you the first 10 results. Think of it as a pager. You know, when you search Google, you're not going to get all of the results on one big long page. That's just kind of not technically feasible. So Google's only going to give you the first 10 results. So then it's going to give you a pager at the bottom, or you can go to the second page of results and the third 10 and the fourth 10. And an API is the same way. It's only going to return to you by default the first 10 results. And then if we want to go to the next 10, we need to add a page parameter, okay? And so if I go back, I know that you can't see my window here, but if I go back to the documentation, I can see that there is something called a page parameter. And the values that it takes is from 0 to 100, okay? So let's go ahead and start putting that in. Now, this value, whatever I'm going to enter, can go from 0 to 100 inclusive. Okay, so I can put in 0, I can put in 1, I can put in 2, I can put in 3. So notice here that the pager starts at 0, which is a common programming convention, but not a universal one. So R, for example, doesn't start counting at 0, it starts counting at 1. But Python starts counting at 0. So the first result is actually index 0. And New York Times works the same way. The first page of the results is actually page 0. The second page result is page 1. Okay, so this will actually return the second, put that in caps just to emphasize, that will get us the second page of results. Okay, now let's, just for emphasis, we can see that our URL has changed once again. Okay. So there are other search terms that I think you saw in the documentation. We can use sort, we can search by various facets. Their facets include days of the week, give me only the results that are on a Monday. Only the news desk, give me all the results that are from the World News Desk or from Metropolitan or from sports or from entertainment. And we can search for the month, the year, and so on and so forth. Okay. And various other APIs will have something similar. So for the Twitter API, for example, you can search for tweets only from a particular user, only from a particular year if you have the advanced API and so on. Okay. All right, so that's how we make our GET request. And that's kind of it for how to make the actual GET request. What we've done is we've made sure that we've formatted our request in a particular way so that the server understands exactly what we're looking for. Now, the second main task is parsing the response. Right. So let's go ahead and just make sure that I ran that. Okay, so we're going to put the response into a new variable that I'm going to call response. And we have to use a particular function for this, which is the content function in the HTTR package. Okay. I'm just putting this HTTR : because I might have other packages that has a function called content, but I'm interested in this particular function, this particular package. Okay. And then I'm going to give it my GET request. And I'm going to tell it the kind of response that I want. I just want the text of the response. Okay. And let's go ahead and just take a look at this. All right. So we're getting a bunch of kind of information here. Let's actually look at the first 1,000 characters. Oh, that's the same thing. Never mind. But this is going to be within this response is going to be kind of the information that we want. But I'm seeing an empty docs. Let me just make sure that I have this set up properly. This is the joys of live coding. Okay. What I've done is I basically have just taken out those queries that we just made. And that's because I was getting actually an empty set, meaning that I wasn't getting any articles back. And that's because there were no articles published that mentions John Mearsheimer in 2005 that involved the second page of results. And so that's why I had to go back and take away those parameters, and so that we actually see some results that we can parse. And so now I'm seeing a lot more text, and this is what is in JSON text. Okay, so it looks really messy. Our goal now is to try to parse this into something that we can actually use for analysis. So our end game is that we want to create a data frame where each row is an article. Okay, so as I mentioned, this is in JSON text that's encoded in plain text. JSON stands for JavaScript Object Notation. And you can think of JSON as like a nested array that's built on key value pairs. So if you're familiar with dictionaries in Python, or if you're familiar with arrays in a variety of programming languages, JSON is kind of like that. But we want to translate it from this very nested tree into something that's just two-dimensional. And so the JSON Lite package is what's going to help us with this. So I'm going to create a new variable called response_df. That's going to be a response data frame. And I'm going to use the from JSON function to basically convert information from a JSON to a data frame. So I'm going to put in my response. I'm going to put in this flag simplify data frame. I'm going to set that equal to true. And I'm also going to use another parameter here, flatten. I'm going to set that to true as well. And that's because some of these key value pairs can be nested on multiple levels. Okay, so if we look at our environment here, we'll see that we have a new object here called response.df, and it's a list of 3. Let's go ahead and just take a look at what that's all about. So I'm going to use the structure function, which is a helpful function to understand the structure of an object. Let's take a look at the first 3 levels. Okay. So we see a lot of information here, a lot of key value pairs. And it has various names. So the first is going to, information is going to be status. We're going to have a copyright information. We're going to have the response information. Let's go ahead and just drill down. This kind of looks intimidating, but it's really just a big old nested list. So let's just see what we have in there. Okay, so at the top level, we have these 3 parts of information, status, copyright, and response. Let's take a look at one of those. Let's like to take a look at the status. Okay, so you'll see that the status parameter just gives an okay. And I think pretty sure that's just information to tell the server that your GET request was okay. So that's boring. Let's take a look at the copyright, see if that's of interest to us. All right, well, it just says copyright 2021. That's also boring. So then let's look at the final name, which is the response. Okay, that looks like information that we're actually interested in. But that's a big long list. So let's drill down even further. So you'll see that even in the response, we have doc and we have meta. Let's go ahead and see what meta is all about. Okay. So you'll see that meta has a few information on the metadata of our search. Namely, the most important thing is hits. So hits returned 150, What does that mean? It means that in our original request, we're searching all articles that mention Mearsheimer. That overall search has a total of 150 hits. So that's going to be helpful. Now let's check out docs. And instead of just calling this because it's going to be big and messy, let's see the names of the items that are in there. Okay, so here's all the information that comes with docs. We have the abstract, we have the web URL, snippet, lead paragraph. So this is actually all the information about each individual article. And this is actually what we're really interested in, right? So let's go ahead and save that into its own variable. Okay. And now you'll see here up in my environment pane that docs is actually a data frame where each row is an article and each column is information about that article, like abstract, the specific URL pointing to that article, a snippet of the article. It'll give you the lead paragraph. It will give you the section of the newspaper. It'll give you keywords, publication date, the news desk, and a lot of other kind of interesting information. Right. So kind of what have we done so far, just to sum up? We have constructed a GET request. We're searching for all the articles that mention Mearsheimer. We formatted that GET request properly. We got a response. We were able to drill down into that very messy object and find the information that we're actually interested in. But we only got 10 articles. And we know that the original response said that it had 150 hits. So we have a total of 150 articles, but each request only gives us 10 articles. And so what do we need to do? We need to create 15 requests. Okay. And each request is going to iterate over each page of the results. And so this is kind of a classic programming task. We want to loop through each page of the results, collect the articles, and then merge them all into one big data frame. And so that is a job for iteration. Okay, so how do we iterate? Well, the first thing that we want to do is let's go ahead and just turn what we've done so far into a function. And so I'm going to create a function here. And this function is going to take a term, a search term, and a page of results of that search term. Okay. And I'm in this function, I'm just going to adapt all the code that we've written so far. Okay. So remember that the first thing that we need is a base URL. We're going to send the GET request. So again, this is just code that I have walked through before. Instead, except for searching for Mearsheimer, I'm generalizing this into any search term. And, oh, excuse me. I'm going to put in my API key, which I've already saved in an object called key. And I'm going to put in the page, instead of putting in a specific page, I'm going to put in the page argument that we're going to pass into the function. And so this was going to construct some GET requests, and we're going to get a response. So again, what did we do? We used the content function to extract the text of the response. We simplified that using the from JSON function. And then we're going to return. Remember, we drilled into that big messy object, and we found out that the documents actually live in this particular part of the object. Okay. And remember that this is going to be a function, and we're going to iterate through each page. And so I find it helpful to add a little print statement that tells us what page we're actually iterating in at any given time. And so I'm going to say we're scraping page and then whatever the page is. Okay. So let me just at this point take some questions. How can we search for the articles which have 2 or 3 words together, not only one word? So for example, the articles that have Mearsheimer plus Germany plus Europe. Yeah, that's a great question. So I would want to look back at the documentation, but I'm pretty sure that if you wanted to search for it, the only thing I'm kind of struggling with is if you put in, you know, as your search term, instead of Mearsheimer, you put in Mearsheimer space Germany space Europe. I'm concerned that it's going to give you all the articles that include Mearsheimer or Germany or Europe. And that doesn't seem like what you want. You want the articles that include all of those search terms, Mearsheimer and Germany and Europe. And so hold off on that question, and I'll during the break, I'll search for the documentation and see if we can get any clarity on that. It might involve putting in several queries. It might involve putting quotation marks around things, but the general answer is that it will depend on the API that you're using. Even the New York Times API, I've been teaching these materials for a while, and it changed at some point. So that instead of searching, you know, John Mearsheimer as one big long string, it searched for all articles that contain John or Mearsheimer. So we're going to have to look at the specific API to see what convention it needs for these kind of multiple search terms. What does the term equals null in page do? So remember, we're writing a function, and this function accepts certain things and spits out certain things. So what it's going to input is some search term and then a page of results for that search term. And it's going to spit out those results that fit those parameters. So let's actually try it out, and I think this will be made a lot more clear. Okay, so we defined our function. So let's try it out. Let's put in, we're going to call our new function, and the term is going to be, let's search for Mearsheimer, and let's look for the second page of results, or actually the third page of results, because page 2 is the third page of results. Okay. So you'll see here that it spit out something to me that's like a little message saying what it was doing. And now I have a new set of documents that are the third page of results for John Mearsheimer. But I could use this function, you know, to search, you know, Beyonce, you know, the first page of results for Beyonce, or, you know, any kind of combination thereof. So hopefully that clarifies what this function is doing. And yeah, so for the metadata, Luke, can you remind me of that question at the end? Because it's a great question. And I think it's going to be perhaps a little bit more clear once we actually follow through with the lesson and see what we're doing with this. But don't let the lesson end without you asking that question again. Okay. All right, great. Okay, so we have this function here. Let me just go back here. And now we're actually ready to use that function to iterate over each page. Okay, so let's just kind of review what we've done so far. I am going to, first we want to find out how many hits we have. So just for the sake of time, I'm going to paste this in here. So this is a review of what we've done so far. We've set the key in the base. We've sent our GET request. We've parsed the response. And then we can extract the number of hits, the total number of hits. Oh, excuse me. Put in the wrong search term. Okay, so we have 150 hits. And so how many pages do we need to loop through? Well, we can kind of go ahead and do the math. We know that it's going to be 15 pages. But if we were writing a program and we didn't know for exactly how many hits we had, we would want to probably do this programmatically. And so for any number of hits, the number of pages can be extracted by rounding up from the hits divided by 10. So ceiling is a function that just rounds up. And now we have the number of pages that we have to iterate through, which is 15. I am going to first show you one way to iterate over all the pages. So I'm going to be using the map set of functions. If you're not familiar, map is a paradigm set of functions in tidyverse that allows us to iterate over things. And so it's an alternative to using a loop, to using a for loop. We could write a for loop, or we could use map. And I find that map is a lot more straightforward, and the syntax is a lot cleaner, and it's a lot faster than writing a for loop. And so what we're going to map over, what we're going to iterate over, is 1 through 15, right? So we're going to go 1 through the number of pages that we have. Okay. And then we are going to be using our New York Times API. We're going to be searching for Mearsheimer, and we're going to be iterating over each of these pages. And so the correct syntax for that is to use a dot. That dot refers to whatever we're iterating over. Okay. Okay. Let's go ahead and try it out. Oh, why? Okay, I think the problem is that in my code, I actually altered this package. I'll alter this function to run slowly. So this is a same version of the function, but remember we have those rate limits, right? And so we actually don't want to iterate too fast. Otherwise, we're going to hit up against our rate limits. And so the slowly function is just kind of a way to alter any function for a delay. And so I think that's why we are getting this error. Okay, so now we can see that it's iterating over each page of results. And as it's iterating over each page of results, the map_DRF stands for map data frame. It's going to iterate over each page of those results. It's going to collect the documents. And then at the end, it's going to paste all those documents together into one big data frame. So let's check it out. So now we can see that we have docs_data frame. We have 100 observations of 28 variables. Not exactly sure why it's 100 and not 150, but we can debug that later. And so here are all these 100 articles that contain the search term Mearsheimer along with their metadata. So going back to Luca's question, what are we going to do with this? Well, one thing that you might be interested in is how the popularity of any particular subject matter changes over time. So let's say that we're interested in jazz, and we want to try to measure the public attention to jazz over time. Because it's gotten more popular at certain times, it's gotten less popular, then it had a revival. And so using this, maybe a measure of attention is how many articles are about jazz in the New York Times. And so for a problem like that, we don't actually need the content of each article. We just want to know how many articles there are and when they were published and to map those over time. And so this, let's do something like this, but with John Mearsheimer. Okay, so we want to figure out how John Mearsheimer's popularity is changing over time. And so all we have to do is to add an indicator for the year and the month that each article was published in. So you'll see here that in each document, we have a publication date somewhere. Okay. And that publication date is formatted in a particular way. It's year, month, date, and then the time, probably like the morning or afternoon edition or something like that. And so let's go ahead and try to format that in a way that just includes the month and the year that it was published in. So what I'm going to do is I'm going to add a new indicator called date. And here's where LubraDate comes in. So LubraDate is a package that helps us format dates. It's pretty magical. All we have to do is put in the format of the string, date string that we're trying to convert. So this was year, month, date, and then hour, minute, seconds. That's how it was formatted. It's because I spelled it wrong. Okay, so now we have this vector of dates that are formatted in a particular way that LubraDate can understand. And so we can actually extract the months. So let's go ahead and summarize these articles by month. So what we're going to do now is we're going to count how many articles were published in each month. We're going to round down because we don't want, we're going to round down by the day just to aggregate by month. Okay. And let's go also and rename those months. So instead of having, January, February, March, April, we're just going to index them month 1, month 2, month 3. That's going to help us plot it. So now if we look at by month, we have a new data frame that includes the month and then how many articles were published in that month. So now let's go ahead and plot this using ggplot. So on the x-axis is going to be the month, and the y-axis are going to be the number of articles that were published in that month. We're going to, let's just do a scatter plot. So we'll do point. Okay. And let's go ahead and add some axes. So the x-axis will be date, the y-lab will be article count. And let's go ahead and try that out. Okay, so hopefully folks can see here this scatter plot, and we can see that John Mearsheimer's popularity really peaked around 2010. We could use this exact same method for any search term. So if you wanted to see how the popularity of jazz changed over time, you follow this exact same protocol, except instead of using Mearsheimer, you would put in jazz. I'm not going to do that because there's probably a ton of results and it's going to take a long time. But so you might be interested in how popularity of a particular subject has changed over time. Something that I've done using the New York Times API is I wanted to know how many articles were published about each country. I had a paper that was about media coverage of women around the world. And I won't go into the substance of the article, but the important bit is that I needed a control variable for how many articles were published about each country total, including those articles that did not address women. And so how was I going to be able to get that control variable? Because some countries are just talked about more. There are going to be more articles about the UK in the New York Times than there is going to be about like Botswana. And so I used the New York Times API. I iterated through each country and associated search terms, and then found basically by year a count of how many articles were about that particular country in that particular year. So that could be another way that you could use the New York Times API. All those two examples I just mentioned, what we're really interested in is just how many articles there are. But I think I could imagine one using other metadata as well. So if you're interested in a computational text analysis of New York Times coverage, you're not going to get the whole article, but you do get the headline and the first paragraph. And maybe that's enough if for whatever computational text analysis application that you are using. So at this point, what questions do you have? About anything that we've done so far, or APIs in general? So I see a question about Lubridate. Can we use regex? Sure. I mean, that's what Lubridate is doing, basically, under the hood. But why struggle with regex if Lubridate is just so much easier? So that I would recommend using Lubridate just to save yourself from a lot of stress and hassle. But you could certainly use regex or regular expressions to format the data as well. Yes, there's a really interesting idea about using this kind of protocol to do a structured literature review. So there have been a lot of interesting applications of doing an automatic literature review using Web of Science APIs or Scopus to collect the title, the abstracts, the authors, some search terms. One of the things the New York Times offered were keywords. which I have used before, just to see, that gives some kind of insight about to what the article is actually talking about. And those keywords also often involve the specific names of figures that are included in the article, so those might be interesting. I would imagine that one interesting application for a literature review would be to see the network of authors. So you could, and I've seen this, you could collect, a bunch of articles in Web of Science about political science, for example. And then you can run a network analysis using co-authorship. And just so you can see through that what kind of clusters of authors and scholarship constitute the kind of the topography of political science. And I could imagine that you could also use some kind of text analytic framework to do something similar about the themes that are revealed in the title or the abstract. So how will this be different for other APIs? That's a great question, Libby. So a lot of things will be the same. So let me actually go ahead and I'll share my screen one more time. And I'm going to highlight the things that will basically be the same. So let me just go back actually to my function here. Okay. So I'm going to star what's going to be different. Obviously the base URL is going to be different for the specific API that you're using. But all APIs are going to require some base URL. Okay? But the specific base URL is going to be different for each API. Okay. We were talking earlier about these key value pairs parameters, and we were debating whether Q, which stands for query, was universal across APIs. And the bottom line is that I don't know, but I am willing to guess that it's almost universal. So almost all APIs will involve some kind of search term. And will require some API key, but which parameters they allow you to search for and what the names of those parameters are going to be different across various APIs. So you can imagine that for the Twitter API, for example, you might not search a page, you might search for all the tweets by particular users or with a particular hashtag. And so you would pass those parameters into that particular API. So this bottom line is that the specific parameters that you can search for are going to be different across APIs. But you'll often see very similar kinds of conventions and infrastructure. And then, at least in R, so what you're actually going to get is the response. And how that response is going to be structured is also going to be different. So you'll always get some kind of response, whether that response is JSON or whether that response is XML, that's also going to be different for the API. But so you might not have something called response and something called doc, but you will get some kind of object that contains the information. That object is going to be in different formats, but you will be able to parse them in some way, shape, or form, either using from JSON or from XML. So I'm also going to put a star here. Okay. So just to kind of sum up, the base URL is going to be different. The credentials requirements are going to be different. The specific parameters are going to be different across APIs. And exactly what that response is going to look like is also going to be different across APIs. So I hope that was helpful. But a lot of things are going to be the same. You're still going to be able to, you're still going to use the GET request library to format that GET request. You're still going to get a response that's going to require some parsing. So, a lot of the really kind of basic steps, I think are going to be quite similar. Yes. Pete, that is the paper that I was referring to. Thank you. How do you get a token? Yeah, so you would have to register with each specific API. And so we posted a link earlier about the page to register for an API token for the New York Times. It's pretty easy, the New York Times one at least. You just kind of fill in a form and then they, with your name and the name of your project, and they'll spit an API access token out at you. For some other APIs require more information, like your phone number. But my basic protocol practically when using APIs is that I'm first going to search to see if there's a plug and play package. So let's say I'm interested in the Spotify API. I'm going to search Spotify API package R and see if there is an R package that already wraps a lot of these kind of functions and wraps a lot of this code into more usable functions for me. So I'm first going to do that. If there's no plug and play package, then I'm going to search for the API documentation of Spotify, and there will usually be some link like get started or register or something. And I'm going to get an API token, and then I'm going to find their documentation, and I'm going to read their documentation, and then I'm going to go into R and basically adapt some of the code that I already wrote for you to search for exactly what I want. So with that, let's go ahead and take a break. We'll take our 15-minute break now. And let me just give you a preview of what we'll be discussing when we come back. So we're going to leave APIs behind, and we're going to go to web scraping. Web scraping is significantly messier because we're not going to get this really nice structured response and structured kind of protocol in order to get our information. So we're first going to kind of dive into what websites are all about, how we figure out their structure, and then we'll be doing another demonstration. But if you have any questions about APIs in the meantime, go ahead and throw them in the chat, and we can address those when we come back. This will be a 15-minute break. So we will return, let's see, it's Chicago time right now. It's 10:53. So we can get back at 10 minutes past the hour. So we'll say 10 minutes past the hour, whatever hour you are in your location. Hi, welcome back, everybody. So I'm going to start by addressing Renato's question, or excuse me, Jenica's question about multiple search terms. This was a question that came up during the last session. And I did a little bit of research into it. So reading the New York Times article APIs overview, I'm in the section called filtering your search. And I can see that it says the article search API uses Elasticsearch, which is some protocol that I don't know. So the filter query uses standard Lacune syntax. Separate the filter field name and value with a colon and surround multiple values with parentheses. And the default connector for values in parentheses is OR. If you declare an explicit Boolean value, it must be capitalized. You can filter on multiple values and fields. What does this mean? What I think it means is that, let's say, remember that we're going to put in our search term in R using a named list with the Q name. So if we search something like jazz and then band, that's going to search for all articles that mention jazz or band. If I wanted to search for articles that mentioned jazz and band, I have to do something like the following. So I have to use multiple quotation marks. Oh, I pressed enter too quickly. And I forgot the last quotation mark there. But you'll see in the second, I put in first an opening quotation mark, and then I put jazz in a single quotation mark, followed by and in capital letters, followed by band in another single quotation mark. So then I closed it all out with double quotations again. So I have not tested this, but that is my understanding from reading this documentation, and I hope that helps. I think if you wanted to search jazz band as one term, so the second is going to give you all articles that mention jazz and band, but they could be anywhere in the article. If you wanted to search something with the phrase jazz band, I'm fairly certain that you're going to have to put all of that in its own quotation marks, such as the following. So I hope that helps, or at least gives you a direction to go in. So Renato, if you could use the same API in The Economist and Financial Times, no, because those are different publications. But if The Economist and the Financial Times might have their own APIs that you can use. And I see that there's a question about metadata that I can't seem to find. Yeah, Janica, I know you. Oh, yeah, so the question that I asked to be reminded about, I addressed in the last session. The question was, what can you actually use with these metadata? So I offered two ideas. One is that you could just look at the publication date and inquire into how many articles were published about a particular subject matter over time. And you could also probably use other metadata to see to get some insight into what the content of those articles are, like the first paragraph, the title or the headline, and the keywords that are attached to it. Okay, so let's pivot and we can talk about web scraping. I'm going to go ahead and start sharing my screen. Okay. So ping me if you can't see this purple slide, but let's dive into it. So I started class by saying that there were two ways to get data off the web. We've already talked about web APIs. Those APIs are a way to structure the internet that is application facing. So they're kind of originally designed for computers to talk to one another. And then there are websites. And these are the things that we're used to as humans interacting with. So these are user facing. They're designed for people's eyes, not for computers' eyes. And I suggested that you use and check to see if there's an API first, because if there's an API, what it means is that there is a database that is designed to be queried. There is infrastructure and a path there for you to collect information in a very structured way and in a consistent way. And websites are neither structured very well, nor are they consistent. So we're always, and there are also legal implications as well. So generally speaking, if you can get the information using an API, you should. If there are no APIs available, then we can scrape a website directly. Web scraping does have some benefits over APIs. One is any content that can be viewed on a web page can be scraped, period. By definition, almost. If you can see it in your browser, then you can scrape it. It might not be easy. The server might try all sorts of tricks to prevent you from scraping it. But purely technically speaking, it is possible to scrape anything that you can see in a browser. You don't need an API. And there's typically no authentication that's required or rate limiting that's required. That said, that web scraping has a lot of challenges. Websites are not designed to be scraped. Okay, APIs are designed to be queried. You don't make an API unless you want people to use it. Websites are not designed for Rochelle Terman to write a program to scrape it. It's designed for users, for people's eyes. And so they are messy, they are unstructured, they are inconsistent, meaning that one part of a web page or subdomain can be formatted one way, another page on that same website can be formatted a different way. Or they might change their structure at any given moment. Which means that your site is going to break, or excuse me, your web scraping program is going to break at some point. And each site, most importantly, each site is going to be different, very, very different. We've seen with APIs that there are some, things that are specific to an API, like the queries the fastest that you can search for, and the parameters and the base URL, things like that. But the basic infrastructure is the same. You're constructing a URL, you're making a GET request, you're parsing the response. And they all kind of tend to use very similar conventions, like Q stands for query. Websites are not like that. There's dramatic variation in different websites. And so your scraper that you write for one website is not going to work for another website, not even close. Okay. And so all of this is to say that is challenging and that APIs are preferable. I have to give some disclaimers first. So you should check a site's terms and conditions before scraping. Almost all sites have terms and conditions at the bottom of the page that will specify what users can and cannot do with the content including information about whether you can scrape it. Even if a website allows you to scrape it, we should be courteous, we should be polite, and we should be ethical about it. And that means that we don't want to hammer the site server. We don't want to take advantage of the content. We certainly don't want to sell the content unless you want to get sued. And we generally just want to be kind of courteous to the website and to the other users on that website. There are various legal implications here to web scraping. And because I'm not a lawyer, I cannot give guidance on that. But I will say that it varies across countries. And it's also an area of the law that is in constant rapid development. So in the United States, for example, there was recently a ruling that was really important that basically said that if a website is available for human eyes, then it should be available to scrape, as long as you don't sell that content. But your country and your legal structure might be different. And so please don't scrape any websites unless you know that it's okay and legal to do so. All right. So in order to web scrape, we have to understand really well what a website is. Okay, so Olga, just you asked a question about robot.txt. The game describes the pages, then you can scrape them. It's a little bit unclear what that means, like if they are allowing you to scrape them, or if it's legal to scrape them, like which authority here is kind of allowing you to do that. But I will say that some websites will try to be able to detect whether whatever entity is calling them up for content is a human or a robot. And they will sometimes try to block robots. So that's kind of where robot.txt kind of falls in. Okay. And generally speaking, like backend server developers will, there's this constant cat and mouse game about a backend server will develop some kind of technology that will try to block web scrapers and robots. And then robots just get more sophisticated, but I mean, they're robots crawling the internet all the time. That's how Google, constructs its search database, is by sending robots to crawl the internet. And so if a website completely blocks robots, it's probably blocking its ability to show up on a search page as well. But I digress. Let's go back to what a website is. We're all familiar with websites. What are they exactly? They're some combination of a code base or a database that lives on a server somewhere. So a server is just an ugly computer that, is, at least in the United States, is like on a farm out west somewhere. And on that computer, just like you have files and data on your computer, on that server lives files and some database, maybe, that constitutes a web page. So a website is nothing but a collection of files and perhaps some database. But when it gets to us, meaning the front end, we're the front end, it's delivered to us as HTML and possibly some CSS style sheets and maybe some JavaScript. Okay, that's it. All websites. Now that Adobe Flash has, retired permanently, thank God, all websites are some combination of HTML, CSS, and JavaScript, period. It could be created on the back end using Python or with Drupal or PHP or whatever. But when it gets to you, it is always HTML or CSS and or JavaScript. Okay, so here's some example of HTML, the first few lines of HTML of Wikipedia. So remember, we were talking in the last unit, we make some requests, we call up Wikipedia. Hey, Wikipedia, can I see your front page? Wikipedia says, okay, Rochelle Terman wants to see our front page. Let's send that to her using HTML. It comes on my computer in HTML, and then my browser turns it into some nice format that I can understand, okay? So the core of a website is HTML, hypertext markup language. HTML defines the structure of a web page using a series of elements. So those elements tell the browser how to display the page by labeling certain pieces of content. So it's going to say, this is a heading, or this is a link, or this is an image. It's going to kind of wrap those content into those labels and then tell the browser how to structure those elements. So one kind of pop quiz that I like to say is, what markup language am I writing in right now? Meaning these slides. And one, if we were a smaller class, we would kind of go back and forth on this. This is kind of a trick question in some ways, because I wrote the slides using a language called Markdown, R Markdown. But that Markdown was then converted into HTML. So you're reading HTML, these slides, you can see that I'm looking at them in a web browser, and the document type is .html, but I wrote them actually using Markdown. Okay. So it is super easy and trivial to pull HTML from a website. I can give you one line of code that you can use right now to download an entire website. Super easy. It's much more difficult to parse that HTML to find the information, the exact information that we're actually interested in. And so let's actually, using example, let's go to Google, google.com. Come on, Google. Don't want to cooperate with me, huh? Okay. Okay. This is google.com. Pretty simple website, right? You wouldn't like, how much content is there? It's like pretty white and pretty blank, maybe a few links. HTML is probably pretty simple on this page, right? Well, in Google Chrome, you can go to view and to developer and to view source. That will basically show you what the HTML plus CSS plus JavaScript is at the back of a particular site. And you can see that this is all of the stuff that comes with that very simple website. Okay. So the point of this is that even though something might look really simple, you never know kind of what is actually the HTML, CSS, and JavaScript that underlies that website. Right. So the basic structure of HTML kind of looks like this. So it always starts with this tag called doctype.html, and then it will structure each element in those labels, right? So this is the title of the website, and you can see that it's surrounded by these title tags. This is a paragraph, and you can see that it's surrounded by these paragraph tags. And it's structured kind of like that. HTML is constructed like a tree. Each element of each branch of the tree is called an element, and HTML elements can contain other elements, just like a nested tree. So here we see that the body element contains a header 1 and a section and a footer element. Within the section element are 1, 2, 3, 4 paragraphs. Within each of those paragraphs, we have bold text, emphasized text, and so on. And each HTML element is structured the same way. It's first defined by what's called a start tag. And then it has some content, and then it has an end tag. So in this example, can everybody see my cursor? I forgot if Zoom actually shows that. Can you see my cursor?
Yes, we can see it.
Okay, thank you so much. So at the top here is the HTML tag, and at the bottom is what will actually format and show up on your screen. So it's just text with some italicization going on, and all the tags contain these triangle arrow bracket things, and so the brackets with an I basically says, okay, start italics, web browser. Then it contains some text, and then it will contain end tag, which is basically the same thing as the start tag, but it has this forward slash here. And that says, okay, stop the italics, okay? And one important thing that I want to emphasize is that an HTML element is everything from the start tag to the end tag. It's not just the text. So when I refer to an HTML element, I'm not talking about just the text. I'm talking about that front tag and that end tag and all of the elements that are inside that element. Here are some common HTML tags. HTML, is one of these things that are, it's like HTTP. It's defined by the internet gods, whoever they are. And here are some common HTML tags. There we have page headers. The body holds all of the content. Paragraphs are P tags. Those are just kind of regular text. We have header text, header 1, 2, and 3, different levels of headers. OL is an ordered list. Excuse me, you'll see that I have a typo here. Those should be surrounded by brackets. UL is an unordered list, basically like little anything that's not numbered. So that could be like a little dot or a point or whatever. And then LI is an individual item that's either in that ordered list or an unordered list. Links are very important to web scraping because we're going to be collecting a lot of links. Are structured in a particular way. They are always start by an A tag. So an A tag means link. And they also have what's called an href attribute. So an href attribute says it defines the URL that the link will point to. And then the text that follows is the text that you see that is pink and underlined. We have table items. And then we have just kind of big general containers that could mean basically anything. This is just another visualization of an HTML page structure that is a more visual demonstration. And you can see here that this header tag is inside of a body tag and precedes a paragraph tag and so on. So some HTML elements can have what are called attributes, and attributes provide additional information about that element. Attributes are always specified in the start tag. So they're always in the start tag, and they always come in a key value pair. So we were talking about key value pairs earlier with APIs. Now we're seeing them again, where we have some key, and that is set to some value. So the most important attributes are probably the link attributes that I was just mentioning. So in the link attribute, we have an href attribute. That's the key, and that is set to some URL, which is the value. Okay, so this is important because the name of the game with web scraping is that we want to drill down in HTML to find the elements that we want and to shoo away all of the elements that we don't want. That is basically the primary task of web scraping. And sometimes we can find the data that we want just by using those HTML tags. So for example, we can tell find me all of the A tags on this page. And that it's going to spit back out at you all of the links that are on the page. And that can be very helpful. But oftentimes that is not sufficient because even an extremely simple website can easily have hundreds, if not thousands of A tags on a page. And we don't want hundreds and thousands of links. We only want certain links and not other links. And so how do we find only the elements that we're interested in? Well, this is why enter cascading style sheets. So CSS stands for cascading style sheets. CSS defines how HTML elements are displayed. So HTML defines what is displayed on a website. CSS defines how it's displayed. A little history here, HTML came first in the history of the internet, but it was only meant to define content, not to format that content. So there are ways to format HTML using tags like font or color, but that's a very inefficient way to develop a website. Some websites can easily contain, 100 individual pages. What are you going to do? You're going to go through each one of those pages and make, something pink or whatever. It's just extremely inefficient. And so to solve that problem, CSS was created specifically to just format content on a website. And now with CSS, we can change the look of an entire website just by changing one file and not going through each individual page. And so the reason why this is important is because a lot of web designers will litter their HTML markup with a lot of CSS to provide that CSS are what's called hooks, namely classes or IDs. They'll provide hooks for their CSS. And you can piggyback on those hooks to jump to the parts of a website that contain only the data that you want. And so this is going to seem like a lot of information that I'm going to spit out at you. I'm not expecting you to become experts in HTML and CSS, but it's just important to get just a general intuition. So CSS has a particular syntax and structure. And the way that it works is that for a particular element, let's say an A tag, remember A is an HTML tag, we can refer to it using a CSS selector, okay? So a CSS selector is just a bare letter or tag name. So A is going to hook into all of the A tags on a page. P space A is going to hook into all of the links that are inside of a paragraph. Okay? And you can kind of continue that. If you want to find all the links that are inside of a paragraph, that are inside of another paragraph, you would do P space A. We can also hook into HTML using what are called classes and IDs. And so if we wanted to write HTML, an HTML element, that it's a link, we can add an attribute where we're defining the class of that element as blue. And by doing that, we can then use CSS to hook into that element with .blue, okay? So A.blue would find all of the links with the class blue. .blue is going to find all elements with the class blue. IDs work in a very similar way. The only difference between an ID and a class is that a class can contain multiple HTML elements on a given page, and an ID refers to just one element. This is what CSS actually looks like if you open up a CSS file. Which is basically we have that hook. So H2 is going to say, hey, we're going to create a rule that's going to apply to all of the H2 tags and elements on this website. And then we're going to define certain things about it, like the color and the font size. We don't have to worry about that for the sake of this workshop because we're not writing CSS. But we are going to use it to find certain elements on a page. So this is an example website. the HTML of that website. And I want you to find the CSS selectors for some elements. So what if we wanted to find the CSS selector for the entire table? So this is going to render into a table. And what if we wanted to find the CSS selector that's hooked into that table? Or what if we wanted to hook into the CSS selector that contained just the row Curtis McCoy? Or what if we wanted to find the CSS selector that contained the element, just the elements containing first name? Let me walk through the solutions here, because I was given that this is such a large class. So if we wanted to find the CSS selector for the entire table, we could actually use multiple solutions. So one is just table. That would work. We could also use the class content. So you could use table or you could use dot content. If we wanted to find the row containing Curtis McCoy, we could, so here's Curtis here. We can use the ID Curtis. So that would be hashtag Curtis. And then if we wanted to find just the first name, we could use the class first name. So here are, again, the CSS selectors for the whole table. Here's the CSS selector for that row, Curtis McCoy. Here's the CSS selector for the elements containing first names. Okay. So we're not going to become probably experts and fluents in CSS, but we can use CSS to find out how a website is structured. And there's a really helpful tool here called Selector Gadget. Selector Gadget is a browser plugin that works with Google Chrome. I'm sure it works with Firefox. And it helps us find HTML elements and then kind of spit out the CSS selector that refers to those elements. So what we're going to do is we're going to use CSS selector to click on the information that we want and only the information that we want. So let me show you an example. This is a very dumb website that I made for the purposes of this class. And what if we wanted to find the CSS selector capturing all the rows in the table? So we we're interested in only the rows of the table. We're not interested in the whole table. We're not interested in the headers. We're just interested in the rows. So my selector gadget is this little magnifying glass up here. I know that's kind of small. I'm not sure if you can see it, but I'm going to click on that. Okay, you'll see that a little window popped up. And I'm going to start by clicking on some information that I want. So I'm interested in that. And you can see everything in pink, or excuse me, everything in yellow is referred to using TD. So TD is the CSS selector that refers to all of those rows. What if I was interested in the whole table? Well, I would then want to click on more information that I want. And so this will give you another CSS selector that refers to that whole table. Let's take a little bit more complicated example. So this is the website that we're actually going to be, part of the website that we're going to be scraping. And let's say I want to find the CSS selector that only refers to that title. So I typed out my my selector gadget here. Even just typing it, it already shows us that it's going to be H1. But let's see if there are any other H1s on this page. No, so that we got our solution is just H1. What if we wanted to find the links for the categories and attributes? So I'm going to click on that. So you'll notice that after I click on that, everything turned yellow, then that's going to refer to everything on the website, but we don't want that. So we're going to click on things that we don't want. So I don't want that. Okay. And I also don't want this file under either. I just want the links. Okay. But it's only giving me this. So I'm going to continue to click on that. All right. So now everything in green and yellow is referred to using the CSS selector. So that's how we're going to find the information that we want on a website. And putting this all together, the basic strategy of web scraping is that we're going to use that Selector Gadget to see how the data is structured on a website. We're going to pay attention to what HTML tags and CSS selectors refer to the information that we're interested in. We're going to pray to the internet gods that there's some kind of pattern that underlies that information. And then we're going to use R and some modules like rvest to extract just that data and to iterate most likely over multiple pages. Okay. So I know that that was a lot. I think this is going to become a lot more clear once we kind of dive into the code. Yes, and then we're going to cry if there's no pattern. We're going to give up. But thankfully, most websites these days are created using some kind of content management system like Drupal and WordPress, and those automatically kind of pattern a particular website. So that's good. But if you know, older websites are going to be harder to scrape because they tend to be not as structured. Okay. So let me show you the website that we're going to be demoing today. So the American Presidency Project is a great kind of nonprofit website that contains an archive of presidential documents. It's hosted by UC Santa Barbara. It has a lot of records about American presidents. Over 143,000 records on presidents and non-presidents like vice presidents, first ladies, things like that. And let's say that we're doing a project on space exploration, which has kind of gotten back into the news lately. And so we want to collect every record there is from presidents that mention space exploration. Now, once I put in that search term, I see some other filters. Let's add, instead of giving us 25 results per page, let's give us 100 results per page so we can see more of them. And okay, there are 346 records. So this is one example of a record. This is the first record that mentioned space exploration was in 1958, apparently. Special message to Congress relative to space science and exploration. This is one record, and you'll see that it has some information. It has the president, it has the title of the document, the date, and then it has the content of the actual record, which is his speech. Okay, so let's say that we are interested in collecting those pieces of information, the president, the title, the date, and the content for all 346 records. That's going to be the project that we're going to complete in the next hour. But again, I want to emphatically plea that you not follow along because if we all ping this website, it's going to go down and we're going to be rude. Okay. So this is going to be our basic strategy. We're going to take this in 2 steps. Okay. And I think this basic strategy applies to every website that I've scraped, at least. So there are actually 2 kinds of pages that we need to scrape here. We need to scrape the results page, right? we need to scrape specifically the links to each document. We need to find the links to each document. And there are 100 results on this page, and there are 4 pages of results because there's over 300 documents, okay? And then for each one of those documents, we actually need to scrape the document itself. And so we're going to do this in 2 steps. We're first going to scrape one document, just one individual document, and collect the name of the president, the title, the date, and the content. And then we're going to put that into a function and use that function to iterate over each one of these results, okay? There are actually going to be 2 kinds of iteration here, though. We're going to have to collect all of these links, and then we're going to have to iterate over each page result as well. But the basic 2 steps are to create a function to just scrape one individual page, and then use that function to iterate over each search result. Okay. Are there any questions about anything that I've covered in the last hour, especially the goal of the project? Okay, well then let's go ahead and go to our code. Give me 1 second to set up here.
Rochelle, there's one question from YouTube. Do the
Oh, sure.
selectors differ according to the browser used?
Yeah, that's a great question. They shouldn't. Yeah, because they're defined on the back end of the website, not the specific browser. However, I will say that different browsers might display that CSS differently. So the CSS and the HTML are going to be the same, but they might look different visually across different browsers. Web browsers, like if you use any kind of modern web browser, Firefox or Google Chrome or Safari, you really shouldn't have a problem. If you use, Netscape, circa late 90s, like you might have some difficulty with how things are displayed. But for the most part, besides very minor, I think, trivial differences, they should all look very similar, and the CSS is going to be identical as well.
Thank you.
Okay. All right, so I'm going to go ahead and start sharing my screen. I'm going to share my whole monitor because we might want to flip back and forth between the RStudio and the website itself. Okay, so remember, we're going to do this in 2 steps. So the first step is that we're going to write a function to scrape each individual record. And then the second step, we're going to use that function to loop through all the results and collect all the pages. Okay. All right, so let's start by loading some of our essential packages here. Again, we're going to use tidyverse. We're going to use something called rvest, which is a function that's also in tidyverse but doesn't load automatically. Rvest is really similar to beautiful soup in Python. If you've ever used that, it's basically just a way to parse HTML and kind of navigate HTML. We're going to be working with a lot of strings, so let's use stringer. I think per actually comes up automatically with tidyverse, but per is going to help us loop through things. And then we're going to also use looper_date to handle the dates in these records. Okay. So our first step is that we're going to use rvest to read the HTML of a specific page. Okay, so what rvest allows us to do is to collect the HTML source code of a website, read that HTML into R, and then also parse it and select and keep only certain elements of the page that we're interested in. So we're going to write our function using just one sample document. And let's go ahead and use that document that I was just referring to, this first guy. So I'm going to use the function read HTML, which kind of does what it says it does, and putting in the URL of the HTML that I want. So let's just take a look at the object that we just created. Whoops, if I spell it correctly, that would help. Okay, so you can see that it doesn't show everything, but this is the first chunk of that HTML document. And it is pretty messy, and we're going to have to use rvest to make that information more usable. So let's find the page elements that we're interested in. So rvest allows us to find elements using a few different things. It allows us to find elements by their HTML tag. It allows us to find elements using HTML attributes, search by attribute, and it also lets us search using CSS selector. You can also use XML selectors as well. And it's very similar to CSS actually, but there wasn't much use in teaching both today. So I decided to teach CSS because I find it to be a little bit more helpful, but you can also use that as well. Okay, so let's first search for by tag. So we're going to use the function HTML nodes, and that's going to find all of the elements, they're also called nodes, in our document that has the tag A. I'm sorry, I said XML, and this is also referred to as an XPath. Okay, so let's take a look at this. So you'll find that what this does is it searches for all of the links on this website, on this one little website. And that's a lot. There are a lot of links. We don't even know how many there are because it cut us off. So we don't want to have all of those links. Let's say that we're only looking for a specific link. Let's say that we're only looking for the link that refers to Dwight D. Eisenhower. So let's go ahead and try to find the CSS selector for that. So I'm going to go up to my CSS selector. Everybody can see my Google Chrome at this point, I hope, because I'm switching back and forth here. So I'm going to click on Dwight D. Eisenhower. So you'll see that it's going to give me the A tag, A selector, which is going to refer to all the links, but I don't want all the links. So I'm going to start clicking on yellow things that I don't want. Okay, and the result it gave me was .diet/title space A. So that is the CSS selector that refers to just the link containing the president's name. I'm going to copy that. And let's go ahead and put that into our function. Okay, this looks a lot more promising. Now we just have one link and one element, and you'll see that it returns the entire element. We don't actually want the entire element. We just want the text of the element. And so we can pipe that into a function called HTML text. So because rvest is part of the tidyverse universe, it supports piping, which is very helpful. And so now we have drilled down and just gotten the name of the president. So great, let's save that into an object called speaker. And just as a sanity check, great, we've collected the speaker. All right. What if we wanted the href corresponding to that speaker? Let's say that we're not actually interested in the name of the speaker, we're interested in the URL that that link points to. Well, there is a rvest function for that. Instead of collecting the text, HTML text, I can use HTML attr or HTML attribute. And then I can just pass in the name of the attribute that I want. So I want the href attribute, and it'll return to me the value of the href attribute. Okay. So believe it or not, that's pretty much all we need to scrape a website. Are those two simple functions for the most part: HTML nodes, HTML text, HTML attributes. So let's go ahead and start collecting some other information. So we have our speaker. Let's collect our date. Okay, what is the CSS selector for the date? Let's find out. Okay, here's my date. Okay, and it automatically came up with the right answer here. Date.date dash display dash single. Okay, then I'm going to go in here and pass that in. Again, it would help if I spell things correctly. Okay, great. It's giving us an element. And remember that we just want the text of that element. So we're going to pipe that into HTML text. And now we've gotten the string character for the date. I'm going to do one more step and pipe this into a looper date function just so that it's all formatted the same. And again, the way that the looper date functions work is that you see what format the date is in, and then you use that to call the correct function. So this is formatted, so the month is first, and then the day, and then the year. So I'm going to put in month, day, year. And now we have a correctly formatted date. Okay, so we have our date. We have our speaker that we've already done. Let's do the title. All right, let's go to our selector gadget to find out what the CSS selector for the title is. Okay, so it's guessing H1. I just want to look around and make sure that there are no other H1 tags. Let's pipe that into, like, we're only going to be interested in the text. Great, we have the title. And then the last thing that we really need is the body of the document. We can call that text. Let's find out what the CSS selector for that is. We want that guy. So this is going to get the P tag. And let's see if there are any other P tags that it's collecting. So you'll see that if we just put in P, it's going to give us all this other junk too. We don't want that. So we don't want that. We just want the body of the record. Okay, that is going to give us actually a character vector. I'm going to make a slight adjustment here. I think this will probably work better. Nope, okay. So because we're getting a character vector, I am going to use a stringer function to concatenate all of that into one long text. Hopefully that will work. Let's see. All right, great. So I just had to add one more step, a stringer function. So instead of giving me a vector of 20 paragraphs, I just kind of pasted it all together, concatenated it all together into one field. Okay. So we have all of our elements. Let me go ahead and just check the chat really quick. Yeah, just to looking good. If you want to do this in Python, I actually have materials for a very similar workshop that's in Python. So you can always email me after class and I'll send those to you. But it's very, very similar. You just use Selenium, or excuse me, not Selenium, a Beautiful Soup. I would not recommend using Selenium for a site like this because you don't have to, and you should never use Selenium unless you absolutely have to. That's my recommendation because it's overkill, but we don't need to use Selenium because there's no HTML on this website, or excuse me, there's no JavaScript on this website. And so we can just use a straightforward Beautiful Soup in Python to basically do the exact same thing, to search by CSS selector or XPath or other things. Don't you need collapse equals space instead of collapse equals T? Well, let's look at the documentation. So if you go to this documentation here, you will find that, yeah, collapse is an optional string used to combine input vectors into a single string. So I thought that it was actually a Boolean, but it looks like it's actually wanting a string. And so I think it's probably exactly right. Actually, instead of, so what collapse is going to do is that instead of collapsing all of these elements in a character and separating them by a space, let's actually separate them by a line break. I think that would probably look a little nicer. So it's going to see //n here, but if we print this out, it's going to be a line break. But we could use a space as well. Thank you, Felix. Okay. All right, so now that we kind of have all of our elements together, let's go ahead and create a function. Because remember that we want to do the same process across all of the search results. Let's call this function scrape doc, because it's just going to scrape one document. And this function is going, what is it input? What is it output? Well, I think it makes sense for it to input a URL of an individual page because that's what we started with. And eventually, we are going to return all of these elements. Give me 1 second here. Just bear with me. Thank you for your patience. Okay. I just wanted to make sure that this was consistent. Whatever I call things are going to be consistent with the materials that were going to be released after the workshop so that no one gets confused. And I wanted to make sure the names were consistent. So whatever we're going to return, let's just pretend like it's going to be some object called return info, or excuse me, all info. Okay. So now we're just going to repeat what we've done, except instead of passing a specific URL, we're going to pretend that it is some attribute that we're going to pass into a function. So what did we do first? We read the HTML. Let's refer to that as just doc, and we're not going to read in this specific URL. We're going to read in a general URL that we're going to pass into the function. And then let's collect the speaker. Let's collect the date. The title and the body of the document. Okay, so we have all these objects, and let's combine them into a list. That's going to, functions can only return one object, and so we have to combine all of these variables and objects into one. So a list is a pretty good kind of all-encompassing container for lots of different objects. So let's name this list. And so our speaker is going to be, we're just going to add the names that are the same as the name of the objects. Okay. And I'm going to call this all info. And let's go ahead and run that function. So like any time that we're running functions that we're later going to be iterating over multiple things, I always like to add some kind of print statement, just so I know, what specific item we are iterating over. So let's add a print statement. And let's add the title, whatever we're scraping. Okay. Oops. Not what I wanted to do. Run that. Okay, and let's go ahead and test this. Let's test it with another document in our results page. Let's go for the singular document by Richard Nixon. I guess Richard Nixon wasn't into space exploration. So we can just pass a URL. It would probably help to save it into some kind of object. Let's call it doc2. We know that it works, that's good. And now document 2, we have all of the information that we need, except it's still saying Dwight Eisenhower. So what did I do wrong? Thank you, Bitan, for warning me earlier. So I'm not looking for document 1. I specified this in another name, doc. let's try that. Okay, this is looking a little bit better. Now we've collected all the information about this particular document by Richard Nixon. So let's go back, kind of take a step back and remember what our basic goal and our strategy was. So remember that we first wanted to scrape or write a function that scraped one document. And now we want to use that function to scrape all 300 and some articles, okay? So how do we do that? Well, first we need to have a collection of URLs that we need to iterate over. So this is one URL of this particular search result, but we need all of them. So we need this one and this one and this one and this one, all 100 results on this page, and we have to iterate over the pager to find the next 100 results, and the next 100 results after that, and the next 100 or some results after that. So let's go ahead and write a function that will do that. So the first thing that I'm going to do is, so just to take a step back, YouTube, is it possible that looping is not possible because every document is built differently? Yeah, great question. If each document is built differently, then you're absolutely right that looping is not going to work. Thankfully, that's kind of what we were saying earlier about like praying to the internet gods that there's some kind of pattern. And luckily, this particular website has a pattern such that all the documents are structured the exact same way. And that's probably because it uses some kind of content management system like WordPress or Drupal or something in the back end. And so thankfully, looping with this function is going to work because all the documents are structured the same way. But you're absolutely right. It's going to be something that you have to check beforehand. Okay, so the first thing I'm going to do is just find that CSS selector that corresponds to these links. Okay, that gives us all the links. We don't want that. We only want the links to these documents. Okay, I'm going to save that for later. And remember that we're going to eventually have to loop through each pager. And so I'm going to just start by writing a function. Okay. So we know that, for example, if we use the read HTML function and pass, that particular URL and that particular CSS selector, we're going to get all the links on that page. It takes a little while. But we're going to have to iterate through each page. So let's start our function. Get rid of that. And we're going to call this function scrape URLs. And that is going to take some kind of URL path of search results. And we're going to basically kind of go through the same process that we did earlier. So the first step is that we have to read the HTML of the whole page. Okay. And then once we do that, then we can go ahead and select those document specific URLs. I'm going to call those links. Oops. That was the CSS selector corresponding to each individual document link. One important thing to remember here is that we don't actually want the entire element of those links, and we also don't want the text of the link. We want the attribute of the link, right? Because it's the attribute of the link that's going to give us the URL that points to each individual document. So we covered this a little earlier. We can use the HTML attribute function to just find the href attribute. And then we're going to return those links. Right. I've defined that function, and let's go ahead and try it out on the first page of the results. Let's call this just a test.
There's an E at links.
Oh, thank you. Okay. So let me copy and paste just that first page of results. And try that out. Oh, it's because I didn't actually redefine this function after my typo. Okay, let's take a look at scrape test, see what this gets us. So we already see that here at the character vector, that's 100. That's a good sign, right? That's what we were expecting. We were expecting 100 URLs. And lo and behold, we have 100 URLs. Was there a question that I missed? Okay. So we have all the URLs for one page, but remember that there are 4 pages of results. So there are different ways that you can approach this problem. Because there are only 4 pages of results, maybe you just manually want to enter in, each page. And call it 4 different things and concatenate it. I don't think there's any shame in doing that. If you had something like 100 pages of results, that would get pretty tedious. And so you might want to add another loop through each page of results. So one way you could do that is to use the CSS Selector Gadget to find each link that corresponds to each page of results. Another thing you could do is to try to look at the pattern of the URL. Oftentimes with pagers, each page on a search result like this will be formatted in a very similar way with regards to the URL. So for example, this is the first page of results, right? What does the second page of results look like? Okay, so does everybody, can you look at that and see what the difference is? Go ahead and put it in the chat if you can see what the difference between those two things are. Yep. In the second page, we have this extra bit here called ampersand page equals 1. If that looks similar to our APIs lesson, that's actually not an accident. Because RESTful APIs are very similar to web browsing in such a way. So we can derive from this one of what Regina said, which is that the first page starts at 0 because this is the second page. And so if we wanted to get the third page of results, we could just kind of change that to 2. And let's see if that will give us the 3rd page of results. Okay, we got the 3rd page of results. And so we've noticed that there's a pattern here. And so we can actually use that instead of going through the Selector Gadget and finding all the links, etc. We can just kind of use a simple stringer function to find all the search pages. And we're going to use string C again. We're going to add everything except for the thing that we're changing, right? And then we want to go from 0 to 3 because that will give us 4 pages of results. And now we have a character vector of 4 URLs corresponding to each page of results. Okay, so now that we have that, we can use the function that we wrote a few minutes ago to scrape all the URLs from all the pages of the search results. We're going to store that in an object called all URLs. And because we're looping, I'm going to use a map function here. And we want to store it eventually as a character vector. What are we looping through? What are we looping over? Well, we're looping through all the search pages. What are we applying to each item in the loop? Our function scrape URLs. That's going to take a few seconds. Uh-oh. Let me try one other thing. This is the beauty of live coding, is that you also see live debugging. Okay, that executed. Now if we look at all URLs, how long is it? 346. That's a good sign, right? Because we have 346 search results, and now we have 346 links. Regina asked, what if we don't know how many pages of search results there are? Yeah, that's a great question. So I found out just because I looked at it, and it's hard for me to imagine a situation in which where you would need to figure that out programmatically. Maybe I'm wrong, but it's hard for me to imagine a scenario in which I would want to derive that programmatically instead of just passing it in as a single value. Maybe if you're scraping something that has multiple search terms, for example, and you're scraping one search term and then going back and scraping another search term, and they have different number of pages. I don't know. But in this case, it's much more straightforward to just look and eyeball and see how many page results there are. But if you really needed to figure that out programmatically, there are kind of different ways probably that you could do it. I would imagine that if you can find using a CSS selector, just the links to the page results, then you can see how many elements there are, and how many elements there are going to tell you how many page results you have. But that's kind of just off the top of my head. I hope that answers your question, Regina. Why doesn't the first one show that as page equals 0? Yeah, good question. It's just because they're aliases. It's just 2 URLs that point to the same page. And so this is a very common web building convention, is that the first page of results doesn't have that page attribute in URL. But if you did pass that page attribute as 0, then you're going to get the same thing. It's kind of like the same thing as the APIs, right? If we didn't specify what page we wanted, it was just going to give us the first page. But we could also specify that we wanted the first page. And so the same, basic principle applies here. That if we don't specify a page, it's just going to give us the first. But if we wanted to explicitly say, give me the first page, we can set the page parameter to be 0. Okay. So let's review. What have we done? We have a function that scrapes an individual document. We have a character vector of all of the URLs pointing to all of the documents. Now, what do we have to do? We just have to iterate over each one of those URLs. But there's a problem. What's the problem? Let's try it with one. So let's take a look at the first thing that we have. Okay. So this is the first URL that's given to us. This is what's called a relative URL. Okay. We know that it's a relative URL because it doesn't start with www dot something. A relative URL will always correspond to the main domain that we have. And so that relative URL is identical to http://www.presidency.ucsb.edu. That's the main domain. And then we can put in that relative URL. So notice that we can't just put in this relative URL into our web browser and have it work. It's going to give us a 404 error. We need to actually pass in a full URL. So we have to append we have to convert those relative paths to full paths, which is fairly simple to do using this stringer function. So let's call this all full URLs. And again, we're going to use a concat function. We're going to pass in the main domain here. And then our vector of relative paths. And that should give us something that does not work. But if I put in the right function, then we should now have 346 legitimate paths that we can pass into our function. So now we have everything that we need. We have the full path to each document. We have a function that scrapes each individual document. And now we just need to iterate over each one of those paths and collect all the information. So I'm going to call this the final data frame. This is going to take a while. So we're looping through all of the URLs that point to each individual document. And in each iteration, we're going to be using the function scrape doc. Okay. And we're going to output this as a data frame. Okay, let's try it out. So because I put in that print statement inside the function, I know where we are in this loop, which is really helpful. Otherwise, you would just see, a red stop button, but you don't know if it's hung up on something. You don't know what it's doing. But now I actually know exactly what it's doing. That it's and actually see which item in the iteration that it's on. So eventually, that is going to bind all of the information to a data frame. How many rows should the data frame have? Throw it in the chat for me. How many rows should our final data frame have? 346, exactly, because we're having 346 search results. How many columns is my data frame going to have? And I like to think these through, actually, just because it helps with debugging if I know exactly what to expect. So how many columns am I going to have? Five. Well, we're going to have the text of the document. We're going to have the speaker. We're going to have the date. And we're going to have the title. And so there should be only 4 columns, unless the way that this function works is that it adds the URL of what we're iterating over. But I'm expecting 4 columns. How did Rochelle create multiple rows with the same line number? I'm a little bit unclear about what the same line number refers to.
My guess, sorry,
Yeah, go ahead, Olga.
My guess it's like the number 1 in the print, so that's probably what they refer to. But I double checked and.
Oh, this, yeah. Like in the print statements, why do they all say 1?
Yeah, I think that's what's the question is about. But
okay.
I'm not sure.
Yeah, well, I'll answer that question, and if our question asker was referring to something else, they can specify. But this is a convention of our studio and R, is that any time that it's printing a vector of any length, it's going to start with this 1 bracket, and then let's say you have a character vector that is 100 items. So it's going to print each item, start with 1, and then at some point it has to loop around because the window is only so big. And so that second item, you're going to see something like 10, so it's going to show the first 10 results, and then it's going to loop through, and then you'll see a bracket 10, and that's because it's starting on the 10th item, and then it'll loop through, and it'll start on the 20th item, so it'll start with 20. And because we are only printing a character vector of length 1, right? Because each print statement is just spitting out to us 1 string, which is the title. Then it's always going to start with 1. It's kind of a weird R Studio kind of thing. Do I ever get blocked from a website when scraping it? It's extremely common for this to happen. And ways to avoid it, you have to understand why you're being blocked. So one reason why you might be blocked is because you're just hammering their server so much. So as I mentioned earlier, there are various tools and techniques that web developers use to prevent, robots or scrapers or DDoS attacks or whatever. And one sign that something is a bot and not a user is if it is clicking around your site so much that it's clicking around like 100 times a minute. Human users rarely click around or ping a website 100 times a minute. So if you are getting a GET request 100 times a minute, you can be pretty sure that it's not a human that is requesting, that it's a bot, and maybe then you can block their ISP. So that could be one reason. And one way to get around that then is that you put in a pause for every time that you are making a GET request. So you make a GET request, and then in your loop, you can pause for a second and then do it do it again, pause for a second, do it again. VPNs are not going to help with this issue because the problem is, I mean, I guess you could find another ISP using a VPN, but the real solution here, if that's the problem, is to put in pauses so that it seems so that you can avoid like the detection for robots. If you do have your ISP blocked, then you would have to find another ISP or just chill out. But I like to, you know, these websites are our friends. We shouldn't think of them as adversaries. We should think of them as our friends. And I think if you approach it in that way, like it's not polite to hammer a site server 1,000 times a minute. And even if you can, you shouldn't. And so it's good to put pauses. If there are other ways that a site can detect that it's a robot that is doing this or a computer that's doing this, not as a person. And there are various workarounds. So what I didn't include in the lesson today, but that's included in the materials, is Selenium. And I will show like a brief demonstration of that since we have some time. And that is a great way to prevent blocking and detection. So we'll go back to that question. Okay, so Olga asked, the question was about lines 108 and 109 and where the link is split on 2 rows. No, these are different links. So this is different path. So this is the relative path, and this is the exact same URL, but it's a full path. And we wanted to make sure that all of our relative paths were converted into full paths so that they would actually render in the read HTML function. The way that I was able to do that is using the string C function, which will automatically append this base URL to all the items in the all URL vector. String C is vectorized, so it'll apply that task to each item in the vector. Is there a way to handle or bypass GDPR? I think it's GDRP. Maybe I'm wrong. Cookie banners to get to the website /HTML of interest. So I'm not very familiar with GDRP. I think that, I actually have a student who's working on it, so I know a little bit about it. But I've never scraped a website in Europe or through a kind of a European website where I've had to face this. But I think my answer to that question is going to be very similar to my answer to the previous question about how to avoid detection. And Selenium is going to help with that. Let me just quickly show you kind of what we ended up with here, and then I'll show you a quick demonstration of Selenium before we wrap up. So I have my final data frame, and it has 346 observations, and it has 4 variables. And it's going to probably take some time for our studio to render this. I think my computer is getting a little bit slow. Okay, great. So now we have all of the information that we were looking for. We can save this as a CSV and do our analysis on it. Okay, are there any questions about this exercise before I move to Selenium for our last 10 minutes? So let me switch my setup here. And if there are any questions in the meantime, feel free to throw them in the chat. How should you make breaks in the scraping process? So there are various functions in R that allow you to do this. So in the API lesson, you saw me use the function slowly, which is one way to do it. Or you could just add a kind of a system timeout. I think it's like cys dot time. I am actually going to use that function in the Selenium lesson, so you'll see it then. But there are, yeah, that you can just pass in like the number of seconds that you want or to wait. And you would specify that in the function itself.
There is also a question from YouTube whether you can demonstrate what you mean by pause and the loop. Thanks.
Sure, yeah. I think this will, hopefully we'll get through enough in Selenium that you can see this aspect of it. Thanks for your patience. So we only have, less than 15 minutes, so I'm going to work through this pretty quickly. But just as a reminder, all of these materials are going to be released right after the workshop, so you can work through them again on your own. Okay. So let's say that we're scraping a website like this. This is from West Bengal State Elections Commission. And we want to collect, so it has information on elections. We want to collect that information. And it has a few kind of fields here. It has various districts. It has various polling dates that will show up. So let's say we're interested in Bankura. And then as soon as we hit that, then we have options for a polling date. And we can also, specify different options here. And let's say I want you to pay attention, okay, to the URL. Keep your eye on the URL once I hit get result. It would try this one more time. Okay. So I think the important part in the URL exercise is to recognize that that URL is not changing. So if I put in a different, so I have information here matching my search term, but let's say that I wanted to loop through all of these. So let's say that I wanted to find, I have to put in a search term or excuse me, a polling date. So let's say that I search for something else. There are a few difficulties here. One is that our options don't actually show up until I enter something, right? So like there's this drop-down menu. I have to click on this drop-down menu. I have to enter something. Only once I enter it does the options for polling date appear. And you'll notice that the URL is not changing once I'm moving these things around, even though the information under polling date is changing. That's one challenge. Another challenge is that even though like there is no one-to-one correspondence between like how this URL is constructed and the search queries that I'm passing through. So it's not like, in our API lesson and in the last web scraping lesson, those URLs were constructed with a particular pattern. It was like ampersand search term, ampersand date or whatever. But this is not constructed like that. And most importantly, if we wanted to loop through each one of these things, this is a drop-down menu. It's not like there's a list of links, right? That these aren't links exactly. They're options from a drop-down menu. And so all of this means that our previous strategy of web scraping isn't going to work because our previous strategy of web scraping assumes that there's a one-to-one correspondence between the HTML that you see on your screen and the URL. But sometimes, so if you have one URL, you see one HTML document. You change the URL, you see another HTML document. The one way that gets messed up is through JavaScript. So JavaScript is completely different technology than HTML or CSS, but it was designed for web development. And what it does is it actually dynamically changes the HTML as you are interacting with the website. So if I click on one thing, something appears. If I click on another thing appears. But the URL is never changing, even though the HTML is changing. And once we have that system, any kind of interactivity, our rvest is not going to work, because remember that rvest, we have to pass in a URL and get all the HTML and then parse the HTML. But if something involves or requires some kind of interactivity in order to get that HTML, we're not going to be able to do it using rvest. And so this is where Selenium comes in. Selenium is actually, it's hard to actually describe what it is. Is it a programming language? No. Is it a package? No. It's kind of like an umbrella project that is focused on automating web browsers. So it was originally, it comprises a lot of different things, a lot of different tools and libraries and APIs, but the basic goal is to automate web browsers. Basically to write code that will remotely control a web browser like Chrome or Firefox as if we were a real user surfing the web. Okay, so if with Selenium, we can do things that you would be able to do as a human. We can type in passwords, we can enter search terms, we can go down drop-down menus and check boxes and et cetera, et cetera. It was not designed for web scraping. It was designed for web developers to test their websites on various browsers. But we can use it to kind of level up our web scraping. Selenium is funky in R. We need to connect with Selenium using Java, which is different than JavaScript. It's a totally different programming language, and Java is you need to download Java Developer Kit, and you need to make sure that it works nicely with R. I've only tried this on a Mac machine and the Linux. So if you have a Windows, I've seen a lot of people using Windows trying to use R Selenium, and they run into problems. But all of which is to say, there is a package in R called R Selenium, but it is unlike any R package you've ever seen. If this code looks familiar to you, then there's a problem because this is it's written in like pseudo Java, which is an object-oriented programming language and has totally different conventions and totally different syntax and totally different structures than R. That being said, let's go ahead and just take I really hope this works. This might not work on this machine, I have to admit, because I've only tested this on another machine. Okay, let's see if that works. I'm going to close this out. All right, so the first thing that we're going to do, R is, it's a higher level object-oriented programming language. I'm just responding to a question in the chat. If you dig deep enough, it becomes an object-oriented programming language. But it's also kind of has these layers on top of it that basically kind of makes it more of a functional programming language. And so that's why a lot of people refer to R as a functional programming language and not an object-oriented programming language, even though if you get close enough to the source, it is. All right, so the first thing we're going to do is start a Selenium server, just like a virtual server. We're going to work through. I really hope this works. Yeah, thank you, Olga. Selenium is a lot easier to use in Python. And I apologize, I'm not sure why my computer is running so slowly. But for the sake of time, if you work through this, what you'll see is that once we actually connect to the server, we can open up Firefox. Thank you for installing updates, Firefox. And then we're going to be able to control Firefox remotely in R. So it looks like Firefox is opening up. Okay, so this is Firefox. I don't know if you see, but there's like a teeny little robot right there in the URL. And that's basically a sign that says that this browser is not being run by a human, it's being run by a robot. Okay. And now we can actually navigate in this browser as we would a human. And of course, I'm going to get errors. Yeah, I really apologize because this computer just had to go through a bunch of updates that I was not expecting. And as I mentioned, our Selenium is really hard to use or Selenium is difficult to use in R. But ultimately, we can basically write code that will emulate a person in a browser. So I could navigate to this particular site. I can find elements in that drop-down menu, and then I can click on those elements. So this is kind of an unusual syntax for R, the fact that you have a function that we get to inside of an object. That's a classic object-oriented kind of convention, is that we are using what's called methods. But now we can actually go through and click on things. We can hit buttons. We can even enter data and enter like keystrokes and things like this. So once again, I apologize that it was not quite working for me today. But Selenium is useful, just to sum up, for if you're scraping a site that has a lot of JavaScript that requires interaction. It's also extremely difficult for Selenium to be detected as such. Even though we are writing a script and having a robot, because we're working through a browser, on the server side, it's going to be very, very difficult for the server to detect that it's actually a robot that's controlling the server and not as a person. So it kind of relates to the discussion that we were having earlier. If you are having some difficulties being blocked or that you have to enter credentials and so on, our Selenium is another solution. So at this point, are there any questions about anything that we've covered today? Pete, just out of curiosity, is Selenium, I think you mentioned that it was not working on your machine either, right?
I was having a couple issues the other day. Yeah.
Yeah.
Can it be a browser issue? Like maybe it will work on Chrome, like driver?
So I actually had more difficulties with Chrome than with Firefox. That's one of the reasons why I was using Firefox, is because the binders to Chrome were not working very well. So that's why I had more success using Firefox. But they're also, so there are bindings to Chrome, there are bindings to Firefox, and there are probably bindings to other web browsers as well, Safari, and things like this. Okay, well, in that case, let me go ahead and remind you where these materials are stored, and I'm going to go ahead and make them public and walk you through them.
Thank you very much, Rochelle. There's lots of thank yous and appreciations in the chat and on YouTube.
Oh, thank you all. I'm sorry that we didn't have more opportunities to interact.
There is a question on YouTube about scraping PDF files from the website.
Yeah, there's a simple function in HTTR. I forget exactly what it is, but it saves files. So you basically pass in a URL. All PDFs are going to have a URL attached to them. And so you pass in that URL, and you'll probably have some options about what directory you want to save them in on your machine, but it will kind of automatically download those PDFs and save them. Okay, once again, I'm just going to pass. Oh, thank you, Pete. Beat me to it. So if you click on that GitHub repository, it should be public now. And you'll find kind of all the materials that we walked through today, including the slides and including the demonstration code. Some things, again, that you haven't, that we didn't cover was our tweet, which is a plug and play package to use the Twitter API. And then the Selenium code is in there as well. No promises about whether it works on your computer, but if you get lucky, then you should be able to run through that code as well. Feel free to email me if you would like to see some of these materials in Python, or if you have any additional questions, and have a great rest of your day.
Thank you very much.
Thank you.